Alright guys, so today we're going to talk about integration. So everything we had been doing up until now is what we know as differential calculus. So that is when you're using the derivative, differentials. Now we're going to move into integral calculus, which is we're going to be doing the integral. So we're going to try to motivate this topic as to what does the integral represent and how do we use it. So let's start with a little graph. Let's say a parabola. Let's say the function will be y equals negative, I suppose, x squared plus 4x. So it has intercepts at 0 and at 4. And let's label. And let's say that we would like to know the area under this curve. So the area of this sort of wedge, if you will, or that parabola there. How do we compute it? So one idea would be, let's go ahead and divide this interval. I want to divide it into 4, but you could pick any number of sub-intervals. And let's compute what the function, the value of the function here. So for this particular case, we could plug it into our function here. We get negative 1 plus 4. This is going to be 3. And what we could do is we can form this little rectangle. At the moment, let's just leave it at that. Now for 2, we go up to right here, the vertex of the parabola, which is going to be, if you plug 2, you get negative 2 squared. It's going to be negative 4 plus 2 times 4, 8. So it's going to be 4. Not quite drawn to scale apparently, but let's keep going. Then here, you would get this value. When you plug 3, you're going to get negative 3 squared. So 3 squared is going to be negative 9. And then plus 12. So it's going to be 3 again. So that's what it looks like in the graph, but it's going to be 3 as well. So the graph was not too bad. And then at 4, you would get the value of 0. So you could compute the area of these rectangles. And at the moment, we would get a very, very coarse approximation of the area under the curve, because you see you're missing this part. You're missing this part. And then you're overestimating the area here by this part. So not quite exact, but it gives us an approximation. Let me go ahead and compute the area of this rectangle. So for example, the base of each one of them is 1. So 1, 1, 1, 1. And the height would be 3, 4, 3. So the area of the rectangles, let's call it A sub r for the rectangles, is going to be 1 base times height times 3. That's the area of the first rectangle. Then we're going to have 1, the base, times height, 4, plus 1, which is the base, times height, 3 again, which is going to be 3 plus 4 plus 3, so it's going to be 10. All right. So what would be the actual area? Let me compute it, and I'm going to tell you the actual area. All right, so computing the exact area. The exact area is 32/3, which would be something like 10.67, and we got 10. So even though we overestimated here and underestimated here, we still got a pretty good approximation. But what happens if we do more? And what we're going to see is that if we do more rectangles, our approximation will improve. So let's call this one 4 rectangles. And let's do one with 8 rectangles and see how we do. So let me redraw the graph, and I'll meet you back here. All right, so now I partitioned my interval into 8. So I partitioned it into halves. And how do you know what will be the width of your rectangles, or how you're going to partition it. You're going to have this, let's call this the endpoint B, and let's call this one the endpoint A. So our interval would be from A to B. And what you're going to do is you're going to call that width delta x, and it's going to be B minus A divided by the number n of rectangles that you want. In this particular case, we would have had 4 minus 0 divided by 8 rectangles, or 8 subintervals, and then we got 1/2 for that. And that's why I made my partitions into 1/2. So I would go up, first rectangle, a little deformed there, but let's keep going. Let's try to make it as straight as possible. Third rectangle. And I apologize for the squeak, but not much I can do about it. And then here I don't get 1 because the endpoint is right there. So that's my area, and you see I'm overestimating here a little bit. And then I'm underestimating here. But you see that now is not as egregious as before. So let's go ahead and compute the area this time for 8 rectangles. And we know what the actual, I'm using the same graph, by the way. Negative x squared plus 4x. And we know what the actual will be. It was approximately 10.67, and here we're at 10, so we're very close already. So let's go ahead and look at what we get now when we make 8 rectangles instead of 4. So what would be the width of the first rectangle? Is going to be a 1/2 for the width. Now for the height, I gotta find out what this height will be. So I have to plug it in here. So I would have to get negative, and then the 1/2 square, which is negative 1/4, plus 2. This 2 is going to be 8/4 minus 1/4 is going to be 7/4. So now we cannot avoid doing decimals. Fractions, sorry. So we'll have to do that. Now, this one we had computed already. If you remember from the previous example, or you can go back, we computed this one, and when we were at 1, we had negative 1 plus 4 was going to be 3. All right, so we have that one. So for the second rectangle, I get 1/2 for the width times 3 for the height. So third rectangle, I'm here at 3/2, and at 3/2 I have to compute it again, so I have to put 3/2 in here. So 3/2 squared is going to be 9/4, so negative 9/4, and then when I plug 3/2 in this x, I'm going to have 3/2 times 4 is going to be 6, and then you have 6 minus 9/4. This is going to be 24/4. Minus 9 is going to be 15/4. And I forgot to write my base. This is the height. The base is 1/2. All right, so we got this one, and I didn't write the answer. It was 15/4. All right, let me verify that one for 1 second. All right, so now this one we had computed before is the height at 2, and really that is the vertex of the parabola. So I drew it a little bit off here. This rectangle, you see, I went a little crooked, would have been here. This is the vertex of the parabola, and the vertex was at 4. So we have that value. Whenever we do, so this one we can write down. Width is 1/2, and height is 4. Let's keep going down here for the second half of the parabola. And at this point, when you do 5/2, let's plug it in. We get 5/2 squared is going to be 25/4, so negative 25/4, and then 5/2 here is going to give you 10. 10 is going to be 40/4 minus 25 is 15/4. We had already gotten that one from the graph, you kind of could see it, but nonetheless, you still want to compute it. And I'll show you then, I'm going to record another video as to how you can plug all this on an Excel sheet. So I'm going to do it from my computer at the office so you can learn how to do it on an Excel sheet so you don't have to do it over and over by hand or in your mind or in your brain as I'm doing right now, which is not very convenient. So let's do that. And I just noticed a big mistake here. This was 6/2. That's what I was doing in my head, which is a 3. So let's change that for a 3. It's kind of interesting. We go from 2 to 6, then to 4. Interesting. It was 6/2, but it's a 3. So this one we had already computed when we had 3 before, and that the height was going to be equal to 3 as well. So that one I don't have to compute because I did it in the previous time. All right, so this last one is going to have this same height as the 7/4 before. So let's do that one. So 1/2 of 7/4. And then the last one would be 0 right here. So we don't have to write it, but just so we have some symmetry, I'm going to write it all out. I wrote 8 times 0. All right, so now it's just a matter of multiplying and adding it and see how close we get to that 32/3 as we need. So I'll do it and I'll return, I'll edit and I'll just put the answer. All right, so now I computed it. Very easy to do in your head, of course. No, I had to grab paper. And I got 10.5. This one was 10.67 approximately. I had gotten 10 before, so I got a lot closer. And depending on your application, a numerical approximation like this can get really, really close. And in fact, later in the semester, we're going to learn how to do the Simpson's approximation. So we'll get to that. You're going to get much better approximations. However, our goal is not to do things approximately. Our goal is to get the exact value for that area under the curve. So how do we do it? Well, if I could just keep adding and more and more and more rectangles, clearly I'm going to be getting closer. But somehow I gave you this area without doing that. So how did I do it? So let me explain. So the goal would be that if you call this one, we have 8 rectangles. So if you were to call it a sub 8 to denote that you are using 8 rectangles, and you call this one A4, somehow we would want to be able to do AN, but not just do AN, but let n go to infinity. And that would give us the area under the curve. If we can put infinitesimally thick rectangles under the curve, we eventually would eliminate all this extra and would get closer and closer and closer, and we would actually get the area under the curve. So we will say that the area under the curve is going to be given by the limit as n goes to infinity of an. So now we have to figure out how do we find that an. So I will erase this and I'm going to explain to you how you set up the integral or the sum, for n rectangles. And then next time we're going to learn how to compute it and we'll take the limit. But I'll just tell you how to set it up on this video. All right, so I'm going to use this one for reference. And what's going to happen is, so I'm going to draw the exact same graph, or as close as I can, I suppose. I'm going to tell you how things will change, but we're going to use this one to motivate things. So we get our parabola. I'm not going to mark anything other than the intercepts. And so what I'm going to do is, firstly, I'm going to compute delta x. We already have that. In this particular case now, I'm not picking n to be 8. I'm just going to be picking my 4 minus 0, but I'm going to leave n as n. All right, so you see now the delta x, the width of the rectangles, that I'm going to be multiplying every time because I do width times height and I add them, it's already a function of n. So we already have a dependence on n built in, but more is true. Let's say I want to draw my first rectangle. Delta x is going to land somewhere here, so I'm going to have this width is always going to be delta x. Okay. So where do I pick my height? Well, I start at 0 and I move delta x to the side. So the first height, let's call it C1 if you will. The first height is going to be given by a plus 1 delta x. In our case, a is 0. I'm starting at 0. I start at 0, so I'm going to do a, which is 0 in this case, plus 1 delta x. So if your graph started away from 0, you still start a plus delta x, because that's going to be your first rectangle, the first vertical line. Then you move over, and you're going to be going from a, 1 delta x, 2 delta x. So C2, my second height, I said height, my bad. My second endpoint on the interval. That's what I meant. So my second endpoint on the interval will be given by a plus delta x plus delta x. So if we move over one more delta x, so again another delta x over, I'm going to have C3, which is going to be this position here, C3, and this is C2, and this is C1, is going to be a plus 1 delta x, 2 delta x's, 3 delta x's. If you continue like that inductively, the nth rectangle here, or the end endpoint of the interval will be a plus n delta x. So now, what are the heights? Because I was talking about the endpoints and I said heights, but the heights are given by f evaluated at, in this case, C3. This height right here is given by f evaluated at C2. And this one is going to be given by f evaluated at C1. So the heights are just going to be f evaluated at each one of these endpoints. So the area of the nth rectangle let me change. Ooh, that's disappearing already. Let me change my marker. The area of the nth rectangle is going to be given by the width, which is always delta x, because each one of them, I'm picking them to be delta x, delta x, delta x, times the height. And the height, I told you, is going to be f of Cn, f evaluated at each one of the endpoints. So whenever you want to compute the area of the sum of the rectangles, you're going to be approximating it by saying a sub n is going to be given by the area of the first one, delta x, times f of C1, plus the area of the second, all the way to the last one. And I see I made a little, it's not a mistake, but it's a little bit silly to use the nth rectangle. I should have said the kth rectangle, because it's true for any k between 0 and n. N is the last one I'm using from 0 to n. So let's just not fix ourselves to n. Could be any k. The last one now, the one I wanted to write, is going to be delta x f of Cn. So let's go ahead and do it for this formula, for this function, so you just see how it works. And then we will learn how to deal with these sums in the next video. All right, so in our particular case, we already have delta x. Let me copy it. 4 over n. And then we have that the function, remember the function I gave you was negative x squared plus 4x. So we're going to go ahead and evaluate this sum right here. Oh, and let me write the term ck. In our case, is going to be a, which is 0, plus k delta x. And that then is going to be k times 4 over n. So 4 over n is our delta x, and k, I'm just going to put it on the side. So what I get then, I get the sum of the following rectangles. So delta x times f evaluated at C1. C1 is when k is equal to 1, so 4 over n. The second one is going to be delta x, f of C2, in that case k is equal to 2. 2 times 4, 8. And I keep going like that. Let me put it down here until I get to delta x, f of, and then I'm going to get k equals to n, f of 4. F of 4 was the last one, and I found yet another mistake. I drew the same graph, and I gave you 2 as my endpoint here, even though we didn't use it. But remember, the endpoint was 4. That's what we used, 4 minus 0 over n. So f of 4 represents the last entry. So you start 1, 2, 3, and the nth term is going to be your last endpoint. Now we need to figure out how we're going to deal with these types of sums. So in the next video, I'm going to show you how to deal with sums that involve n and how we're going to add them up. All right, so we will talk about that in the next video. So until then, thank you so much for watching.